In this video, we will be looking at work, energy, and power. This will just be a summary. I'm not going to be solving problems in this video, but in the next ones, that is where I'll be looking at problems related to work, energy, and power concepts. Let's remind ourselves what energy was or is. If you remember very well in lower grades, probably grade 6, natural sciences or technology, there's a point where you had to define a force. And whoever was defining a force said it's a push or pull. And then later on, you had to define energy. And whoever defined this said it's the ability to push or pull. What do we mean by this? We mean that energy is the ability to apply a force. The only way we can apply a force, or anything can apply a force, is if it has sufficient energy. If a force is a push or pull, then the ability to push or pull is energy. Keep this in mind. Now we are going to define work. If I've got an object, a block, and I apply a force F on this object, maybe a force F, and I displace this object from point A to point B. Eventually, the object will land here at point B. Then we can define the work done by this force. Sorry about that. Work done by the force will be defined as WF is equal to the force F itself multiplied by the displacement over which it travels, this displacement here from A to B, right? We also put a factor called cos theta. This factor has a value of 0, 1, or -1 in normal cases. We do not ever work with cases where this factor has a different value from 0, 1, and -1. But we will explain what this factor means. So if I pretend as if this factor is 1, it's 1, and I suppose that my force is 20 newtons and my displacement is 10 meters, then if this factor is 1, the work done by F will be the 20 newtons multiplied by the 10 meters times 1, which should give me 200 joules. The units for work are joules, the same units as energy. Work and energy are very related. Let's talk about this factor here. Now, I may be able to move an object along the path A to B, which is given by displacement delta x, by applying a force F. Now, I want us to notice something. The direction, displacement is a vector. The direction of our displacement is from A to B. In other words, it's to the right. Even this force F is applied in the same direction as the direction of displacement. So what does this mean? It means that the angle between force and displacement, theta, is 0. Now when we are applying that factor, we will say F times delta x, and then the factor will be cos of 0 degrees, because the angle, in fact, they are both pointing in the same direction. When two vectors are pointing in the same direction, the angle between them is 0. There is no angle between them. Okay? But let's suppose that we are also experiencing the application of friction on this object. So let's say friction is this green one. Let's call it kinetic friction. Now kinetic friction is pointing in the direction that opposes the direction of displacement. If we are using the screen, the displacement is pointing to the right, while the friction is pointing to the left. Now they are pointing in opposite directions along the same straight line. That means that the theta for friction is going to be 180. They are pointing along the same straight line but in opposite directions. So what does this mean? It means that if we are looking at work done by friction specifically on its own, then it will be the frictional force times the same displacement, because the object will move over this displacement despite friction pointing in the opposite direction, and then cosine of 180 degrees. Cos 0 is 1, so that is how I decided that my factor was 1 here. Cos 0 is 1. But cos 180 is negative 1. So it means friction will do work in the negative direction, while this force F will do work in the positive direction. Now, we will substitute values when time is right. Your job is to take notes so that when I start working on problems, you can always refer back to these notes. One other force that could be acting, or two other forces, but I'll choose one, is the normal force. The normal force is pointing perpendicular to the surface over which this object is moving. The object is still moving in the displacement from A to B, in other words, delta x, but there is a force pointing upwards, which is the normal force. This normal force, if you look at the direction of the displacement and the direction of the normal force, they form a 90 degrees. The angle between them is 90 degrees. So theta in this case is going to be 90 degrees, and the work done by the normal force will be the normal force multiplied by the displacement and then cos 90 degrees. Interestingly, cos 90 degrees is 0, so it means in moving the object from A to B, the normal force does not apply any work. The object moves from A to B only due to F and Fk. But the normal force, and you will soon realize that even the force of gravity, they are perpendicular to the displacement, so both of these forces will not apply any work in moving the object from A to B. But if the object was moving up or down, then the normal force, or rather the vertical forces, would be the ones that do work. Normally, if the object is hovering up, then we don't expect there to be normal force, but we do expect the force of gravity to exist. So if a helicopter is trying to lift an object upwards, the force of gravity will apply work downwards while the object is moving upwards. But we will deal with those types of problems when we come across them. repeat this as many times as you need so that you can understand what we are talking about. Now, in objects, typically objects experience multiple forces. We've got a force like Fa, like that. We've got a force like the frictional force, or maybe even tension. We've got the normal force. You've done Newton's second law problems. You've worked on free body diagrams and saw what the number of force. You've been able to break down the forces that act on an object. Now, because we have multiple forces acting on an object, we can easily find the work done by each one of the forces. But we may also be interested in the net work done by each of these forces. What do we mean? We mean the total work done by the forces together combined. So what does work net mean, or the net work done mean? It means it's the total work done by all forces in the object. So applied on the diagram. So if we've got the display, if we've got the sum indexed by I, it's going to be the force I multiplied by the displacement traveled by that object cosine theta for the force I. Okay, don't mind this, but if you are doing grade 12 and you've done sigma notation, this should make sense to you. But what I want you to use instead, so that it makes sense to you, is that it means the net work will be the force the work done by the force A, Fa, plus the work done by the normal force, plus the work done by the frictional force, plus the work done by the force of gravity. Sometimes we might want to resolve the net force on its own, F net. If you remember very well, we find F net by looking at the sum of all forces. So we might want to resolve F net on its own and end up writing this formula as the force net delta X. It's going to be the net force times delta X. You can still put a cos theta, but in this case, the theta will always be 0 if you've already resolved the net force correctly. If you resolve the net force correctly, then theta will always be 0, so cos theta will always be 1. Keep these formulae in mind, especially this one. The E is a place where it will work more, but you can freely resolve each force or each work done by each force separately. Now, let's remind ourselves of the forces that we must have, or rather the formulas that we must have come across in lower grades, even as low as grade 9. Now, if we have any object, let's recall, in fact, I'm going to write this in red. Recall any object of mass m moving at v, at a velocity v, will experience a kinetic energy, right? And that kinetic energy will be given by Ek is equal to half mv squared. Now suppose that the object moves from point A to point B, and it happens to have an initial velocity at point A, or the velocity at A, and a final velocity at point B, or the velocity at B. It's still an object of mass m, and it's moving in that direction. Now, this one has a changing velocity. Because of the changing velocity, it will imply that there is a change in kinetic energy, which is just half mv final squared minus half mv initial squared. Clearly, the m, because it's the same mass, is the same, and the half is also the same, so we can factor out the half, and then in our bracket we can have vf squared minus vi squared. Please make sure, if you opt to use this second version of the formula, do not ever make the mistake of writing half m vf minus vi squared like this. This is totally wrong. Now, this is not the only thing that we learned earlier in our studies. We also learned that an object, maybe let me put a star, also experience a force due to gravity. Or rather, yes, a force due to gravity, right? And this then implies that we have what we call the gravitational potential energy. EP will be equal to the force of gravity, which is mg, that is the force of gravity, multiplied by the height of the object. Now let's suppose we are moving this object upwards. It has a mass m from point A all the way to point B, right? The initial height, if this is the ground, the height from A to B, I'm going to call it my initial height. I mean, the height from A to ground is going to be called the initial height, and the height from B to ground is going to be called the final height. Then this implies that we've got the change in gravitational potential energy, and that is mg h final minus mg h initial. We can factor out m and g, they are constants. mg h final minus h initial. Keep these in mind as well. There are no squares here, so please do not apply squares. Now, where were we going with this? We were going towards the work energy theorem. Let me remind you a little bit of what Newton tells us. So, in Newton's law, the Newton's second law in particular, he says that when a net force acts on an object, that object will accelerate. What does it mean to accelerate? It means it will have a change in velocity, right? And then he explains to us how the acceleration works. So directly from Newton's second law, because when a net force acts on an object, the object changes its velocity. In fact, I'm going to write it like this. The acceleration is the same thing as delta V over delta t. You remember this formula from the Newton's second law in terms of momentum, right? This delta V delta t we can multiply by a factor of half, and we will realize that we end up getting the force, I mean the kinetic energy. So I'm not going to get into this, I'm not going to get into the derivation in this lesson, but what I intend to show you is that the net work done on an object, the total work done on an object is equal to the object's kinetic energy. Kinetic energy happens when there is a change in velocity. The only way we have a change in kinetic energy is when we have a change in velocity, right? So we can go ahead and even rewrite this formula. Remember we said work net is F net delta X, and the kinetic energy, the change, is half m, and then Vf squared minus Vi. You will use this formula however it will help you, okay? But this is exactly the same thing. It's the work energy theorem. Write this down. The work energy theorem, the statement for the work energy theorem says that the total work done on an object, or rather the total work done by all forces on an object, is equal to the object's change in kinetic energy. We call this a theorem because it's mathematically true, but it's not physically true. Physically, work and energy are not the same thing. They have the same units, yes, but they are not the same thing. So we can't say work is equal to energy. But mathematically speaking, we can find kinetic energy by resolving the network, and we can find the network by resolving the change in kinetic energy. It's a mathematical statement. Okay, we apply this to solve a lot of problems. From this point, we can now look at conservative and non-conservative forces. Let's start by defining a conservative force. So these are the type of forces that the total work done by these forces does not depend on the path taken. And you will realize that some forces actually do depend on the path they take, but not all of them. So what does it mean? If I have an inclined surface like this, let's call ground our initial, and then let's call the top our final. I can move a block of M along this direction here, and it will kindly just go over the incline. But somebody else can move the same block M directly up like this from the ground to the top, right? Both of these both of these users will apply. I mean, if we have a conservative force, that conservative force will apply the same work in moving over the incline as it would if it was moving directly vertically upwards. That is what we are calling about. I mean, that is what we are trying to say when we are speaking about the conservative force. A conservative force will do the same work in moving the object along the incline as it would when moving the object vertically upwards. As long as the initial and the final is the same, the path doesn't matter. That is what a conservative force is. The example of conservative forces are forces like the force of gravity and the electrostatic force that you've learned, the Coulomb's law type of force that you've learned in grade 11 and that you will still cover in grade 12, right? We have a couple more forces, but not in our scope of learning, so I will just stick to these two. So the force of gravity and this are normally the conservative forces. They do not care about the path taken. And in fact, when you apply these forces over a closed path, if I start here and then I move an object like this and then return it back here, the force of gravity will apply work in all of these instances, but by the time we get back here, it will be as if it applied zero work. You personally know that you carried this object along this whole path, but the force of gravity will not remember that. It will say that because the path was closed, the work done by gravity is zero. But the applied force, on the other hand, the force that is acting upwards or along the same direction as the path, that force will not experience zero work. And that is why we call those types of forces non-conservative forces. So non-conservative forces are forces whose total work done depends on the path taken. Meaning that an applied force, unlike gravity, an applied force will feel that moving along the incline took more work than moving directly upwards or vertically upwards. So an applied force will not feel the same thing. Even friction will say that there is more friction in moving up the incline, or there is more work done by friction in moving up the incline than moving directly upwards. Even forces like tension would feel the exact same thing. They will say there's more work done by tension in moving up the incline than moving vertically upwards from ground to top. So force of gravity specifically will say that the work done by gravity in moving from the bottom to the top through the incline is the same as the work done by moving from the bottom to the top vertically upwards. That is the force of gravity. That is because it's conservative. But the non-conservative force, like friction, like the applied force, like tension, they will say that there is more work done along the incline than when we are moving vertically upwards. So the examples of these are your friction, your tension, and the applied force. Right? There are so many other examples, but we will stick to these ones for now. Right? Now, the work done by a non-conservative force, that is the interesting thing, because we have a formula for this. Remember, we said the work done by a conservative force really doesn't matter too much how we are moving. But the work done by a non-conservative force gives us a formula. It says that work done by a non-conservative force is equal to the change in gravitational potential energy plus the change in kinetic energy. So basically it is the change in mechanical energy that is equal to the work done by a non-conservative force. Normally this answer should come out as negative if that non-conservative force is friction, but it should come out as a positive if it's an applied force, or if the force is in the same direction as the displacement. You will see when we're going over these problems that it naturally puts itself in place. We are almost at the end. I want to define power, or let's start with the conservation of mechanical energy. So if you remember the conservation of momentum, this is almost the same thing, conservation of mechanical energy. Conservation of momentum used to say in a closed system the total linear momentum is conserved. Conservation of mechanical energy will say the same thing. In a closed system, the total mechanical energy is conserved. What does this mean? It means that the mechanical energy initial is equal to the mechanical energy final. The same way as when we were dealing with conservation of momentum. But what is mechanical energy? It's potential energy, gravitational potential energy plus kinetic energy. So gravitational potential energy plus kinetic energy initial will be equal to the final counterparts. So final potential energy plus final kinetic energy, right? And this is the conservation of energy. Know the statement that I said. Rewind and make sure that you understand the statement. And then lastly, I will define power. Okay, let me use a different color. Power is the rate at which work is done. Sometimes you can say it's the rate at which energy is dissipated. So power as a rate at which work is done is going to be basically the network or the work for that particular force we are interested in over delta T, or it will be the energy dissipated over delta T. But we also do have average power. Average power happens when we've got a constant force. It has to do with a constant force. Normally, how will we know? That's if it can be a net force, by the way. We know this because they will tell us that the average velocity is so and so. So the formula for average power is just going to be that force that we are interested in multiplied by the average velocity. We have kindly reached the end of this lesson. These are the concepts that summarize the topic of work, energy, and power, and these are the exact concepts that we are going to use or apply when we come across problems. I hope this lesson was useful, and thank you.